Hi everyone, so this is question 9 that we are going to solve right now. So please have a look at the question. Okay, the question says that the length of a simple pendulum is 75.0 cm. Okay, this is what we call as length. Okay, and it is released at an angle which is 8 degree to the vertical. Angle theta 8 degree to the vertical. Okay, so they ask you to calculate the period, pendulum's bob speed, pendulum's bob acceleration when you pass through the lowest point of the swing. Okay, let's not be too concerned about the question first. Let's try to understand how a simple pendulum works. Okay, this is the first time we talk about pendulum, so let's do a bit of detour to talk about a simple pendulum first. Okay, so simple pendulum usually requires a ceiling. The next thing you require is a string from the ceiling. For simple pendulum, right, we can only assume it's an SHM only if the angle is small. So just now my drawing is inaccurate. The angle shouldn't be too big. Okay, then you have a mass at the bottom. Okay, so this is a simple pendulum, and based on the situation here, they say that the length is 0.75 meter. Then you also know from the description that the angle at which they release is 8 degree. Okay, this angle is 8 degree. Why do they need to tell us that it's 8 degree? Telling us 8 degree, actually the significance is only one thing. It's telling us that it's a small angle. Okay, so if it's a small angle, only we can treat it as SHM. Okay, if it's not small angle, if it's 30 degree, 40 degree, then it's not an SHM anymore. We cannot approximate it as an SHM. Okay, you will learn about this from my experiment. Your experiment, the coming experiment, you learn about small angle approximation, this kind of stuff. Okay, so your pendulum, your simple pendulum, will be swinging something like this. It will be swinging like this, back and forth. Okay, so there are many ways of deriving simple pendulum, but I'm going to derive it following the book Young and Friedman. So if there's a little bit of difference, you have to understand different books derive the whole thing differently. Okay, so we can think of the distance from the equilibrium position. Okay, the equilibrium position is here. Okay, if you go down here, this is the equilibrium position. We can think of x, the displacement, as this distance here. Okay, this curved distance, we can call it as x, which is the displacement. So x is not a straight line distance right now, it's curving along the path of the simple pendulum. Okay, as usual, do you remember last time we relate f equals to negative kx and f equals to ma? So it's a similar situation. We want to find what is related to what is the f for equals to ma. We want to find the f right now. Find this. Okay, so to know what is the force that's causing the acceleration, what do? We apply what we learned in chapter 4. We draw the free body diagram when the object is here. So the free body diagram, first you start with a dot. The second thing is probably the axis. For here, I'm going to choose the axis to be 1 along the line, and the other one is perpendicular to the line. I'm going to choose the axis like this. So this one is along the line, along the pendulum line. Okay, then the other one will be opposite. The other one will be perpendicular. Sorry. Okay, so if you start to label the forces, the first thing is the ball has mass, so there will be weight pointing downwards. I'll call this mg straight away. Then you have a string here, then the string causes you to have tension. Tension is away from the object along the string. Okay, you have no external force, you have no surface, no normal, no friction, because they didn't mention anything about rough surface. Okay, you will neglect the air resistance as usual. Okay, so this is the free body diagram for a simple pendulum. But we are interested to know the what's causing the acceleration along this direction of motion. You know the thing we're accelerating in this direction, so we want to know what is the force in this direction. What is the force in this direction? So as you can see, the tension and the acceleration are totally perpendicular, so the tension will not be contributing to the acceleration. What is contributing will be the weight. So if you resolve the weight, you have two components coming out for weight. Okay. The first component will be the one that is opposite the direction of tension. Okay. That will be mg cos theta. Well, you might be thinking, how do I know which one is cos, which one is sine? I'll just elaborate a bit. If you draw this line here, this will be the theta. Therefore, this will be the theta. That's why it's mg cos theta. Okay, the theta comes from here. Okay, so this is not what we are concerned about. We are concerned about the other one. This, the component which is parallel to the acceleration, mg sine theta. So this is the one that is causing the acceleration, mg sine theta. So we can plug in the force to be mg sine theta. But be careful, if you just write mg sine theta equals to ma, then you'll be having problem actually. Why? It's because we are treating x, it should be negative mg sine theta actually, because if you see here, the direction of acceleration is this direction, but the direction of x is in that direction. They are in opposite direction, and the theta is actually turning in this direction. Okay, this direction is actually clockwise, and if you learn in chapter 8, if it's clockwise, it's negative. So it's negative mg sine theta actually. The acceleration and the theta are in opposite direction. That's why you have a negative sign. Just like your F equals to negative kx. Your restoring force and your displacement are in opposite direction. Okay, so this is the equation we have now. Negative mg sine theta equals to ma. Now, if theta is small, okay, small is like about 10 degree, less than 10 degree, we can do small angle approximation. Okay, small angle approximation, it's a property of sine actually. Okay, what does it mean by small angle approximation? Is if your angle is small, your sine theta will be about the same with theta itself. Okay, sine theta is almost equivalent to theta. You can try to key it in. Okay, remember, do it in radian form. Let's say it's 1 degree. Let's say it's 5 degree. Let's say you can try to key in sine 5 degree divided by 360 times 2 pi. Okay, your value here will be quite similar. The result of your calculation, sorry, your sine, your calculation of this will be quite similar to this itself. Okay, only if this is small. Okay, that's the idea behind small angle approximation. Okay, so we know that the angle is small. So what can we do here is, now is negative mg sine theta equals to ma. So theta is less than 10 degree. Therefore, we can do small angle approximation. It becomes negative mg theta equals to ma instead. Negative mg theta equals to ma. The sine theta, we change it to become theta using small angle approximation. Now, if you do a bit of potong, you can potong the m. And now you are left with, a equals to negative g theta. Okay, usually when we want to derive this equation, you want to derive at the end, it should be, you want to compare it with a equals to negative omega square x, right? You want to compare, so you need to have a and x. So now it's in theta, you have a, but this is in theta. You want this to be x. You want to change this to x. So how do you change it to x? If you recall, this is our x. Over here, this is our x. And how do you relate it with theta? You can relate it using this formula. X equals to L theta. Okay, it comes from your R equals to S theta. S equals R theta. It comes from the S equals to R theta. In this case, X is equals to L theta. If you bring this in, what will come out will be negative G theta will be X over L. Okay, so now it will be A equals to negative G over L X. Now you can successfully compare this with negative. You can compare these two equations to figure out that omega square is actually equals to G over L. Okay, this is similar to what we do last time with a spring mass system. Last time it was omega square equals to K over M. Now it's omega square equals to G over L. So since this thing looks quite important, I'll box it as well. Okay, omega square equals to G over L. So that's the derivation for now. If you know omega can be related to big T, so you can find period if you manipulate a bit this equation here. Okay, well, the main thing I want to show is how do you get this thing here. Okay, so knowing that, we can probably start to solve the question. It's a long detour, but I hope you are able to get a little bit more understanding after this explanation. Okay, I know it's a bit messy, sorry about that. Okay, So question A asks for the period of the oscillation. Okay, you know that period of the oscillation is related to your omega. Rearrange it. T is just 2 pi over omega. So what do you know about omega? Omega square is G over L. Therefore, omega will be 2 pi over square root G over L. Okay, here there's a square, but what you need here is omega only. There's no square, so you have to do the square root by yourself. Okay, knowing this, they give you the G and they give you the length, so it's now a matter of substitution. 2 pi over 9.81 divided by the length, which is 0.75. So after using your calculator, press it, the answer you get will be 1.74 seconds. Okay, if you are very familiar with the formula sheet, the formula that you are using will probably look something like this: 2 pi L over G. Okay, you might be using a formula like this. These two things, they are the same. It's just manipulating, arranging the equation. They are the same thing. Okay, but usually I prefer to remember just this thing, and knowing this thing, I can combine them to get 2 pi divided by square root of G over L. So that's the period of the oscillation. Next thing is the pendulum's bob speed. The pendulum's bob speed and acceleration when it passes through the lowest point of the swing. Okay, what do you know about the lowest point? When it's at the lowest point, you know that theta will be equals to 0. So we have this equation. Probably can start from here. We have this equation here, right? Let's probably start from here then. No negative mg sine theta is equals to ma. Now at the lowest point, theta is 0, so negative mg sine 0 is ma. Sine 0 is just 0, so it will become 0. 0 times everything will become 0 ma. Okay, so from here you know that the acceleration is 0 meter per second square. Okay, there are many ways to get why acceleration is equal to 0. Okay, this is my way of doing it. Feel free to find another way. Okay, and as usual, if an object is at the equilibrium position, you know that the speed will be maximum. It will be at maximum velocity. So now, since lowest point is the equilibrium position itself, you can say v at the lowest point will be just equivalent to, just for speed, right? So it will just be modulus of Vmax. Vmax is velocity. If you modulus it, it becomes speed. Okay, so you know Vmax is just plus minus a omega. So now it's a matter of finding amplitude and omega. The amplitude is the maximum displacement. So I think we can label this part here. See the diagram. This part here is just the amplitude. So how do you find amplitude? Amplitude is basically just L times theta when it's at maximum. Okay, again we are using the formula, this formula here, S equals to r theta here. Now the amplitude is equals to L times theta when it's maximum, and you times it with omega. Now it's just substitution, plus minus, the length is 0.75, theta max is, remember, in radian form. This S equals R theta must be done in radian form. So 8 degree divided by 360 degree times 2 pi radian per degree. 2 pi radian per 360 degree. Okay, so multiply this, then multiply it by omega. Let me give myself a bit of space. Omega, as you know just now, is just square root of G over L. So it's 9.81 divided by the length of a string, which is 0.75. Just close it back. So now if you continue the calculation, you'll be able to get the value 0.38 meter per second. So that's the speed at the lowest point of the simple pendulum. There are a few other ways to get this speed when it's at the lowest point. There are many ways of getting it. Let me demonstrate one more way. Okay, I'll use in purple pen probably. The another way is using what you learned in chapter 5, principle of conservation of mechanical energy. So mgh is equals to half mv squared. So how does this thing work is, you have your pendulum like this. Let's see this continue up there. Then when it swings to the equilibrium, it's somewhere here. So there is a difference in height between these two positions. And this is the height travel that you bring in here. Okay, if you are able to find the height here, you'll be able to find the speed. Let me complete this diagram. It looks terrible. Okay, so the thing swings from here to here. And swings from here to here, it goes down by this much. So if you are able to find the h, you are able to get the v. Okay, so how do you get the h? So you need to find h. Basically what you need to do is you take this length until you reach here, you minus this one, connect somewhere up there, then you minus this one. Okay, I'll call this length 2 minus length 1. Okay, so to continue the equation, this will be mg length 2 minus length 1 equals to half mv squared. Length 2 is just the length of a string, nothing special. So it's mg length. Length 1 is actually, this is the angle here, which is 8 theta. So this length 1 here is actually length cos 8 degree. So this will be minus L cos 8 degree. Okay, now this is in degree. Be careful with the conversion later in your calculator. You cancel off the m, you cancel off the m, you have all the values. So if you write in all the values here, your v will come out as 0.38 meter per second as well. Okay, if I skip step too fast, L is just 0.75. This L is just 0.75. You have everything here. You can move around, then you can get V. And the V, you have the same answer as what you get earlier. Okay. There are many ways to get this speed at the lowest point. So I introduced two methods. You can use either one of them. Yeah, this question requires more practice. It's a bit difficult because this is the first time you are exposed to simple pendulum calculation. Okay, so that's it for question 9. We find the period and we find the pendulum's bob speed and acceleration when it's at the lowest point of the swing. Thank you very much.